Hello and good day everyone. My name is Siti Fazila Nur Ain binti Sidi Omar, and today I will present the progress report of my research titled Electronic and Thermoelectric Properties Prediction of Hexagonal Perovskite Ba2CoTeO6 Base Ceramic. Research summary. As we all know, global population growth and rapid pace of industrializations is increasing, therefore facing an energy supply depletion and environmentally populations. So, thermoelectric has been widely investigated as a clean energy conversion technology. However, this thermoelectric has a problem of low efficiency and exactly low values. One of the common thermoelectric material, which is bismuth telluride, has been widely used because it has the best figure of merit. But the problem is bismuth telluride is not resistant to high temperature and high toxicity. So another thermoelectric material has come up, which is the oxide perovskite material, which is becoming more critical as it has been found to have a high temperature durability, non-toxic, and environmentally being nature. So this is the literature review in this research, which is the summary is from the literature is the bismuth telluride is widely used in the industry, however not as resistant to high temperature. And the second one is perovskite is inexpensive to the manufacture, non-toxic, and readily available, and they have excellent thermal and chemical resilience at elevated temperature. Thus, from the literature, the problem statements is the current thermoelectric material bismuth telluride is not resistant to high temperature and high toxicity, and the second one is the efficiency of thermoelectric is very low. So the first objective for this research is to analyze the electronics and thermoelectric properties of oxide perovskite, strontium titanate, and Ca2FeMO6. So the second objective is to express the ability and the possibility of a credible thermoelectric material in terms of figure of merits. Scope of this study is we are using COMSOL Multiphysics to simulate two different thermoelectric material, which is Ca2FeMO6 and strontium titanate, and to be compared with the common thermoelectric material bismuth telluride. So two different thermoelectric effects will be studied, which is the Peltier effect and the Seebeck effect, which the input data are different with each other. The research methodology, so the thermoelectric was chosen, and the simulation are carried out in a steady state environment. All materials are linear elastic, and all materials are available in COMSOL Multiphysics software and in literature. This is the conceptual geometry, which is there two, a single leg thermoelectric and a single thermocouple, which have two thermoelectric legs. So this geometry model was built in the COMSOL Multiphysics software. The meshings, as you can see, for two model is different, which is based on the literature also. So the mesh is determined using the swap mesh approach, and the matching pattern of the geometry was manually specified to increase the accuracy and save calculation time. And the input data for the the simulations for the Peltier effect, the input data is the inward current, and for the Seebeck effect, the input data is the temperature difference. So data collection and analysis for the single leg Peltier effects. So the first is the temperature distributions. As you can see in the graph, the perovskite material show a heating effect, while the bismuth telluride show a cooling effect. For the electrical distributions, both perovskite produce a higher voltage, which is due to the higher electrical conductivity of the perovskite material. Second is the variations of the thermoelectric lakes, which is the optimizations simulations. So the temperature distributions, as you can see for the both material, so the temperature difference of the thermoelectric for both material increase with increasing TE height, and the temperature of the Ca2Fe-MOO6 produced is higher than strontium titanate due to the difference of the thermal conductivity and the internal resistance of each material. For the electrical distributions, so both have a linear increment, and as the height of the TE lake increases, the voltage output also increases. The third simulations was the single leg Seebeck effect. So for the temperature distributions, we can see that bismuth telluride show a faster increment of the temperature compared to the both perovskites. In the electrical distributions, we can see the highest is the strontium titanate produce a higher voltage than the other two material. For simulations, the single thermocouple Seebeck effect. So as you can see in the picture is the temperature distributions. So we can see that different material give different impact. Bismuth telluride has a higher thermal conductivity, thus it shows smaller temperature gradient, resulting in a lower percentage of thermoelectric converted energy. And the second result that was the power output of each of the material. So we can see from the tables that strontium titanate showing a higher power output compared to bismuth and Ca2Fe-MOO6. And from this table, we can see also that the power increase as the temperature difference increases also. Thus, it's open up the possibility using the material. In higher temperature TEG derivatives. So the status of the data collections and analysis. So there were 5 simulations. So most of the simulation is 100% completing with the analysis, except for the single thermocouple Peltier effect. For the list of publication, there are 2 papers published in 2022 by Transient Publisher and IEEE. For status of thesis writing, 100% on the research methodology, while literature is 70%, and introductions and result discussion is 30% and 50%, and haven't done the conclusions yet. The future work of this research is completion of the thesis and LOI form submissions, and another one is the simulation of the Peltier effect for the thermocouples. Thank you.